Hey everybody, it's Tuesday, November 3rd, and as you can see here on the AIM today, our main focus for this video is going to be to prepare ourselves to use Newton's laws to analyze physical systems. So, as you probably remember, over the course of the last bunch of days, we have been going through all three of Newton's laws. And now that we have covered all three of Newton's laws, now we're ready to get to the part of this dynamics unit here where we apply those laws to solve a bunch of different problems. And so today we're really going to take a look at how you are going to do that in a little more detail. But first, we have to wrap up what we said about Newton's third law because we didn't quite finish that up yesterday. So yesterday we started talking about Newton's third law. And when we were talking about Newton's third law, we basically said whenever any two objects interact, because an interaction is always between two objects, whenever two objects interact, they exert equal and opposite forces on each other, no matter what. So anytime you see one object touch another object, they exert forces on each other, and those forces are equal, and those forces are opposite. And that's really it as far as Newton's third law is concerned. Just they exert forces on each other, and they're equal, and they're in the opposite direction. We also asked a pretty important question, which was about why those forces don't cancel each other out. And what we said about why those forces don't cancel each other out is because they act on different objects. And so the reason why the forces don't cancel each other out in a Newton's third law type of interaction is because they don't act on the same object. And forces can only cancel each other out if they act on the same object. Now, the last thing we ended up talking about before we wrapped it up in yesterday's video was about the normal force. And what we said was that when an object sits on a surface, like this book sits on this table, the book has a downward force of gravity acting on it. But of course, the book doesn't accelerate downward through the table because the table is there. And so what we said was, well, if the book has a downward force acting on it, but the net force is zero because the book is not accelerating, then that means there must be an upward force acting on the book. And that upward force is the normal force. So the normal force, we said, is a force exerted by a surface on an object which is perpendicular to the surface. So the normal force is actually a force exerted by the surface itself. Now, the obvious question there would be, well, how is it possible for a surface, like an inanimate object, to exert a force? And it's because the normal force really at its most fundamental nature is an electromagnetic force. As we discussed yesterday, you have those valence electrons repelling each other in the objects that are in contact. And so we get this force as a result on the macroscopic scale. The atomic level force, when we see these electrons repelling each other, manifests itself as a contact force on the macroscopic scale, which we call the normal force because that force happens to be exerted normal to the surface of mutual contact. And so we said when you draw a diagram of those forces, it ends up looking like this, where you have the gravitational force going down and the normal force going up. And what we can see from that sort of diagram, when the objects aren't accelerating, so the acceleration is zero here because the object is at rest, we see that the normal force is equal in magnitude to the weight. Obviously, they're in opposite directions, and so that's that. And then once we discussed this, we were ready to take a look at some problems. And so we answered some questions on a sheet entitled Newton's Third Law Worksheet number 1. And so now, because we have addressed the problems on the first sheet, we are ready to address the problems on the second sheet. So if you go to this post, you will see an attachment attached to this post called Newton's Third Law Worksheet number 2. And on the front side of the Newton's third law worksheet number 2, you will see a problem called B3WWT57, which we are going to go ahead and answer now. This problem says a potato with a weight of 2 newtons is resting on a table. A student makes a number of statements about this situation. And so notice these WWT coded tasks here are the what's wrong tasks, where you are supposed to say what's wrong about each individual situation and why. And so for the first one, I'd like you to take a look at A and B. And as the problem says, I'd like you to answer the question, what, if anything, is wrong with this statement? If something is wrong, identify it and explain how to correct it. And if the statement is correct, explain why. So the statement for A says the weight of the potato is a force of 2 newtons exerted by the earth in the downward direction. And then B says the reaction force to this weight is a force of 2 newtons exerted on the potato by the table in the upward direction. So I'd like you to take, let's call it 3 or 4 minutes to pause this video here and come up with an answer and an explanation for A and B. And once you've got your answers, hit play and we'll go over it. So let's begin with A. A says A has the student saying the weight of the potato is a force of 2 newtons exerted by the earth in the downward direction. As we said when we were talking about Newton's second law, weight is a measurement of the gravitational force. And the gravitational force exerted on an object when that object is on the surface of a planet is the force exerted by the planet on the object. And it is, from every frame of reference on the surface of the Earth, in the downward direction, because the force of gravity always acts toward the center of the planet. So the answer for A is, this statement is correct. The force of gravity is a force exerted by the Earth on the potato. And because they tell us it's a potato with a weight of 2 newtons, then we know the weight is a force of 2 newtons. So this statement is correct. The force of gravity is exerted by planets on objects. Take a second to pause this video here and amend your explanation if you need to, add anything that you might have had missing. And when you hit play, we'll jump over to B. Okay, so part B says the reaction force to this weight is a force of 2 newtons exerted on the potato by the table in the upward direction. Now, when they're saying the reaction force to this weight is a force of 2 newtons exerted on the potato by the table in the upward direction, the big question here is, what are they talking about? A force exerted on the potato by the table in the upward direction. What are they talking about? They're talking about the normal force. So the question essentially is saying the reaction force to this weight is a force of 2 newtons exerted on the potato by the table in the upward direction. And despite the fact that the normal force is equal and opposite of the weight, the normal force is not a Newton's third law reaction to the weight. This answer is false. The reaction force to the gravitational force exerted by the Earth on the potato is an equal and opposite force exerted by the potato on the Earth. As we mentioned, and we're going to take a second after we're done with this to write some notes about this. As we mentioned, interactions only involve 2 objects. So if the interaction, or specifically here, the action involved in this interaction is a force exerted by the Earth on the potato, then that interaction only involves the Earth and the potato. And I think that using this like phraseology here of exerted by 1 on 2 is because it's nice, because you can, number one, get a sense of exactly which objects are involved in the interaction and know what is exerting the force and what the force is being exerted on. But it's also important to realize it helps you very easily to identify what the reaction to the action actually is. Notice in the action, we have earth on potato, and in the reaction, we just switch the object, potato on earth. Earth on potato, potato on earth. That gives us a sense of what the reaction is. So this statement here is false because the reaction to the force of the earth on the potato is a force from the potato on the earth. Take a second to pause this video here and add whatever may be missing to your explanation. And when you hit play, we'll write a note about that. This question is a good question because there's some very important things revealed by the answer to this question. Let's say a couple things. The first thing we're going to show is basically the answer to that question, which is just a reminder. You don't need to write this down because you basically just did, but an important thing to remember is action-reaction pairs can only include the same two objects. In this case, the earth and the potato, and that's it. The reaction force, in this case then, is the force exerted by the potato on the earth. So, for the note about this, let's say the following. And this is a huge note here. This is very big. Action-reaction pairs can only involve two objects. If you get in the habit of describing forces in words by saying the force exerted by blank on blank, all you have to do to write the reaction force is switch the order of the objects, since the same two objects are the only objects involved. So if you say the force of A on B, then the reaction is B on A on B, B on A, earth on potato, potato on earth. That's the idea. Action-reaction pairs can only involve the same two objects. And what's like super easy about that then is that whenever you are asked a multiple choice question, like on the AP test, about what is the correct reaction to the action being described in the problem, it's the answer choice that involves the same two objects. That's it. And so if the answer choices bring in any other objects besides the two objects mentioned in the problem, then that's automatically wrong. That's an important thing to realize. Take a second to pause this video here and write that down because this is super crucially important. And when you hit play, we'll move on. Moving on in the sheet here, let's go to part C. Part C says the normal force exerted on the potato by the table is a force of 2 newtons. The reaction force to this normal force is a force of 2 newtons exerted on the potato by the earth in the downward direction. Based on what we said so far, this one should be pretty quick for you to answer. So go ahead and pause this video here. Take like 1 or 2 minutes. Based on what we said, this shouldn't be that complicated at all. And when you hit play, we'll go over the answer and then move on. Okay, so C says the normal force exerted on the potato by the table is a force of 2 newtons. That's a fact. It's exerted on the potato by the table. And then it says the reaction force to this normal force is a force of 2 newtons exerted on the potato by the earth in the downward direction. No, that cannot be right. It brings in a third object. So if the normal force is by the table on the potato, then it shouldn't be that hard to figure out what the reaction is. This statement is false. The reaction force to the normal force exerted by the table on the potato is an equal and opposite force exerted by the potato on the table. And that is in the downward direction. You may want to add that on here if you didn't already, because they specifically tell you the normal force is upward, and then they say in the downward direction when they're talking about the earth. This statement is false. The reaction force to the normal force exerted by the table on the potato is an equal and opposite force exerted by the potato on the table. And I would write, if I were you, in parentheses next to that in the upward direction. I said that it's opposite, and so there's not a whole lot of ambiguity there, but we should be crystal clear that reaction force is, in fact, upward. Take a second to pause this video here and write that down, and when you hit play, we'll move on to the last one on this side of the sheet. And lastly, for part D says if the 2 Newton potato is lifted off the table by a hand that exerts a force of 4 newtons upward on the potato, the reaction force to this 4 Newton force is a force of 4 newtons exerted on the hand by the potato in a downward direction. Now, there's a lot there, and the way that's phrased is confusing, so let's read it again. If the 2 Newton potato is lifted off the table by a hand that exerts a force of 4 newtons upward on the potato, the reaction force to this 4 Newton force is a force of 4 newtons exerted on the hand by the potato in the downward direction. Take a second to pause this video here, answer part D, and when you hit play, we'll go over it, wrap this side of the sheet up. Part D says you have this 2 Newton potato being lifted off the table by a hand that exerts a 4 Newton force on the potato. So we have a 4 Newton force exerted by the hand on the potato, hand on potato. And so that means the reaction force should be potato on hand. And the problem says the reaction force to this 4 Newton force is a 4 Newton force exerted on the hand by the potato. That's it. The statement is correct. The reaction-reaction pair involves the same 2 objects. And since the action-reaction pairs are always supposed to involve the same 2 objects, this one is correct. Take a second to pause this video here and write that down, and when you hit play, we'll move on. Okay, so this sheet I like, number 1, because it has a potato in it, and I just think that's kind of funny. But number 2 is because it really sort of focuses you on the precision in the language that you need to have when you're describing these forces in words. And so I really think the idea of just like switching up the objects, switching the order in the sentence while keeping like an overall template, the force exerted by blank on blank, because then you'll never get it wrong. It's like a guaranteed sort of foolproof way of getting these things right. And the key idea here is that the action-reaction pairs only involve 2 objects. And for the next thing we're going to talk about, I think it's really important to make sure you have down what objects are interacting in a particular problem so you know how many forces there are. In the very beginning of this video, I showed this image, and I think it makes sense for a lot of people to think that there should only be 2 forces, the weight and the normal force is the action and the reaction, because there are 2 objects interacting. Like people look at that image and they see the book and they see the table, and so they think, okay, well, there's 2 objects, so should be 2 forces. It's important to realize here, despite the fact that there are 2 objects pictured, there are multiple objects interacting: the book, the table, and the earth. And it's important not to lose sight of the fact that the earth is an actor here. And so really, when you have all of these interactions, you have to consider that. So when we're talking about the book interacting with the table, there are really a lot of interactions going on. And interestingly enough, not even all of them are pictured in this image. So the first thing that we can talk about here is you have the force of gravity acting downward on the book. And so that is a force exerted by Earth on the book. And so the reaction to that is the force that the book exerts on the Earth. So those are 2 forces right there. Then we have, as pictured in here, the normal force, which is exerted by the table on the book. And then we have the reaction to that force, which is the force exerted by the book on the table. What we also have, not shown here, but equally important, is the force of gravity exerted by the Earth on the table. So, like, there are a lot of other forces that we can talk about here. We have the force of gravity exerted on the table, and then that means we'll also have the reaction to that, which is the force on the Earth by the table. So we have the force, I think I might have just said that backwards, but we have the force of gravity exerted by the Earth on the table, and then we have the reaction to that, which is the force exerted by the table on the Earth. Earth on table, table on Earth. We also have the normal force exerted by the floor on each of the legs of the table. So that would be the force exerted by the floor on the table. And so that means we have a reaction to that on the floor downward, which is the force exerted by the table on the floor. Now, the floor is connected to the building, so there are definitely going to be other forces that are acting on the floor. And of course, we're going to have a gravitational force on the floor, and it could go on and on and on. Interactions that look simple, just like a book sitting on a table, which is sitting on a floor, actually have a bunch of forces involved in them. Generally, though, and this is going to be a big takeaway when we get to the next thing we're going to talk about, when we want to analyze the motion of the book, we really only care about the forces that are acting on the book. And that's an important thing to keep in mind going forward. I'd like you to take a moment to sketch this and make note of all the forces that are acting here in this situation, because it should be a main takeaway for everybody that in simple interactions, there are still a lot of forces acting. Take a second to pause this video and sketch that in your notes, and when you hit play, we'll move on. Okay, so just very quickly here before we wrap up Newton's third law, I'd like to take a look at the questions on the back side of that sheet. So looking on the back side of that sheet here, we see a problem, B3 LMCT 58. And this is a problem where we have these toy trucks colliding head on. And it says here, two identical toy trucks traveling at the same speed in opposite directions are about to collide. The magnitude of the force exerted on truck A by truck B during the collision is equal to the magnitude of the force on truck B by truck A. It says identify from choices 1 through 4 how each change described below will affect the magnitude of the force exerted on truck A by truck B during the collision as compared to the magnitude of the force exerted on truck B by truck A. And the choices are, this change will cause the magnitude of the force exerted on truck A by truck B to be greater than the magnitude of the force from B on A, less than the magnitude of the force from B on A, the same as the magnitude of the force from B on A, or indeterminate as compared on truck B by truck A. So it says here all these modifications and changes are changes to the initial situation shown in the diagram. It says here for A, the truck is carrying a heavy load. So if instead of this situation as pictured here, they now put like a big box in the back of this truck here, how would the situation change as described by these choices? I'd like you to take a minute to pause this video here, answer this question, and write up an explanation. And when you hit play, we'll go over it. So it says here that we've got truck A carrying a heavy load, and I hope everybody realized the really important way this question was asked. It says here in the text of the question, you want to identify from the choices how each change described below will affect the magnitude of the force exerted on truck A by truck B during the collision as compared to the magnitude of the force exerted on truck B by truck A. So basically what they're saying is when the force exerted by A on B is a number, what can you say about the number for the force truck B exerts on truck A? And the answer here should be pretty obvious. It's choice 3. The answer is the same. According to Newton's third law, the force exerted by object A on object B is equal and opposite to the force exerted by object B on object A. And that's really it for this sheet. Because notice, in the other questions, when they ask here, truck A is going faster than truck B, truck A is carrying a heavy load and is going faster than truck B, truck A is speeding up or accelerating, truck A is accelerating and carrying a heavier load, truck A is speeding up while truck B is carrying a heavier load, doesn't matter. Newton's third law applies. The forces are always equal and opposite, and that makes the answer for every single question on this sheet choice 3. No matter what. When object A exerts a force on object B, the force object B exerts on object A is equal and opposite. And the big note here, of course, is that Newton's third law says whenever two objects exert forces on each other, the magnitude of those forces are always the same. A on B equals B on A, regardless of whether it's speeding up, slowing down, faster, slower, heavier, lighter, whatever. The size of the force the objects exert on each other will always be different in those cases, right? Like if the two objects are going at 4 meters per second and then they're going at 40 meters per second, the force that they exert on each other will be bigger. But when you're comparing A on B to B on A, the forces will always be the same. I want to make sure that I'm not confusing anybody by the way that I'm saying that. So let me just say here, if the objects are moving at 4 meters per second, the force A exerts on B, let's say that's 10 newtons. That means B will exert a 10 Newton force on A. Now, if instead of going at 4 meters per second, the objects are going at 40 meters per second, object A may exert 100 Newton force on B, but that means B will still exert 100 Newton force on A. When I'm talking about the difference, I'm talking about the difference between the entire scenarios. But if we're comparing the force A exerts on B to the force B exerts on A, they are always the same. And that's a super crucially important thing for everybody to understand. I'm going to go back to the key now. And if you have not written that down, that's super, super, super important. No matter what, the force exerted by object A on object B is equal and opposite to the force exerted by object B on object A. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So now that we've finished here talking about Newton's third law, we're ready to go ahead and discuss the last thing we're really going to talk about today, which incidentally is the first thing and most important thing probably that we need to discuss when it comes to talking about how we can use Newton's laws to analyze systems. As I think I previously mentioned here already, the biggest difference between AP physics and Regents physics in terms of the kinds of Newton's second law problems that they're going to have you solve is that in Regents physics, almost all the time they ask you to use Newton's second law, they say like the force is this number and the acceleration is this number. What is the mass? Or the force is this number. The mass is this number. What's the acceleration? And so on. They make it very easy. There are 3 variables in the equation F net equals ma, and they give you 2, and they ask you for the third. What you'll see in this class is that that's not the situation at all. In fact, while you will see it sometime on the homework, you'll never see it in tests where they say the force is this size, the mass is this size, what's the acceleration? Never going to happen. What they're going to give you are unique situations, some of which you have seen before, some of which you have never seen before. And you will basically need to, using a technique that we are about to discuss right now, make up the equation that describes that particular system. And so now we are really getting into like the big leagues of physics, because these are not going to be like cookie cutter template problems. You'll really need to analyze the situation, make up the equation, and then apply the equation that you made up from your analysis. And what we use to analyze these problems are diagrams of the forces. And these diagrams are called free body diagrams. And free body diagrams are diagrams detailing all of the forces acting on an object. To be clear, this is the most important part of what we're going to be talking about for like the next 2 weeks. Because everything in all of these problems, no matter how easy they seem, no matter how complicated they seem, everything comes from the free body diagram. So take a second to pause this video here and write down that definition, and when you hit play, we'll move on. So free body diagrams are diagrams detailing all the forces acting on an object. And there's a bunch of things that we can say about free body diagrams. One thing that you should note here going forward is that writing down free body diagram is kind of annoying. And so for the most part, I'm going to abbreviate free body diagrams as FBD. This is not particularly a common thing. This is one of my abbreviations. So you shouldn't expect to see FBD as an abbreviation written in a lot of places, but this is just one of mine for the sake of writing these things down quickly. There's a ton of stuff right now that we have to say about free body diagrams. The first thing we'll say is we want to draw free body diagrams because the total force in each direction is going to give us information about the acceleration of each object in each direction. And so when we have multiple forces acting to the left, let's just say, and multiple forces acting to the right, we want to know about how much total force acts to the left and how much total force acts to the right, because that will determine the motion of the object, because it'll give us information about the object's acceleration. That obviously is a fairly important point. This is a huge idea. Objects, as we've mentioned, especially in the context of Newton's third law, objects only experience forces when they interact with other objects. To determine the forces that must be included in the free body diagram, all you have to do is consider the objects with which the object of interest is interacting. So here's the deal. The first thing you have to remember is that the objects are always going to interact with the Earth because they're on the Earth and the Earth exerts a gravitational force on the objects. Like, don't forget that. If you want to figure out how many forces there's supposed to be in the free body diagram, you have to look at how many objects the thing you're drawing the free body diagram for is interacting with. So let's take the example of the book sitting on the table from earlier. If you were drawing a free body diagram for the book, you would include 2 forces in that diagram. How do you know you're supposed to include 2 forces? Because the book is interacting with 2 objects. It's interacting with the table, and that interaction produces the normal force. So that's one interaction, one force. And then the object is also interacting with the Earth. Second object, second force. That's the idea. So objects only experience forces when they interact with other objects. So you want to figure out how many forces you're supposed to put. The main thing you should focus on is just looking at how many objects the thing is interacting with. Figuring this out is really useful because what's kind of complicated in this problem is that Newton's second law holds in every dimension of space. So you're, in some cases, going to have a multi-dimensional problem. And so you'll need to consider the forces that are acting in the x direction separately, the forces that are acting in the y direction separately, and the forces that are acting in the z direction separately. Because, as I hope you remember from projectile motion, the forces acting in each direction are not really going to affect each other because the motion in each direction is independent of every other direction. That's the idea. And so how are you going to figure out the sum of the forces equation and the acceleration? Well, the whole point here is you're using your free body diagram to write an equation for the sum of the forces. So that's how that works. You draw your diagram, You use your diagram to write an equation for the sum of the forces, and then you basically include that sum of the forces equation into the sum of the forces equals ma, depending on which direction you're talking about. A lot of these problems are going to be one-dimensional problems, but as you'll see, like a perfect example of a multi-dimensional problem here would be an object on an inclined plane. There are multiple dimensions there, x and y, because the object is sliding like diagonally down the ramp. So you'll need to use equations in multiple dimensions. Take a second to pause this video here and write these 4 bullet points down, because these things are super crucially important to you figuring out how to solve these problems. Okay, so now we basically talked about like what a free body diagram is and what we're going to use it for. And now we really want to talk about how you're supposed to draw it. So the first thing that we should say here, and this is an extremely large note, free body diagram arrows, the forces are shown by arrows here. So free body diagram arrows always start at the center of the object, which is usually shown on the diagram as a dot, and move away from the center of the dot in the direction the force is supposed to be. So, why am I telling you this? Well, the reason why I'm telling you this, honestly, is because this is just how they're supposed to be drawn. But this is important to remember because this is how the AP test actually scores these questions. So if they're just showing you like an object in free fall, let's say, to just make it as easy as it possibly can be, and they show you a dot on the object in the drawing, if you show the force of gravity like this, you have the force going in the right direction. It would affect the object's motion the way it should. That's wrong, though, because they always give you a point for drawing the force in the right direction with an arrow starting at the dot and moving in the direction it's supposed to be going. And so in this case, it'd be starting from the center of the object going down. The reason why that's true is because you always want to show in these free body diagrams where the force is acting. And the free body diagram shows where the gravitational force is acting in this example here on the right, because the force of gravity always acts at the center of mass of the object. That's just a fact. And so you want to put that at the center of the object like that. Now, obviously, here you do have this arrow pointing towards the center of the object here as well, but it is just a convention that you start the arrow from the dot. And the AP test, even if you have all the arrows going in the right directions, the AP test will take a point off of your response for not having the arrow start from the dot. This is a super important note. Take a second to pause this video and write this down if you haven't already, and when you hit play, we'll move on to the next note. Okay, next big note here. We got 2 important notes about free body diagrams that you should definitely remember. Something that's going to be really helpful about drawing the diagrams is figuring out which way the object is going to accelerate. In 95% of the cases, you're going to look at the situation and you'll be able to tell which direction the object is going to accelerate in. But in some cases, you might not be able to. And so the idea here is, if you can't tell which direction the object is accelerating in, make it up. Just pick one. The free body diagram will take care of the rest. If you pick the wrong direction, your acceleration will just work out to be negative. And if you assume in your diagram that the object is going to accelerate in a certain direction, and then you get a negative number, it just means that it's going the other way. That's no big deal. The other note here is that, and this is very big because they give points for this in the AP test as well, free body diagrams are drawn to scale, specifically like a rough scale, to show the relative magnitude of the forces acting on an object. The way they do this on the AP test is they're going to give you a grid space. And on that grid space, you'll be able to show the rough scale of something. So they'll give you a grid space. They'll mark it off. This is a terrible drawing, but you get the idea. And then they'll put the diagram for the dot at the center. And so if you know that, like, let's say the force of gravity and I'll do this in another color so you can actually see it. If you know the force of gravity is supposed to be included in a diagram, and so is the normal force, and the object is on a flat horizontal surface, you want to draw those things with the same length arrow because you know those forces are equal and opposite. If somebody pulls to the left and somebody pulls to the right, but the person pulling to the right is pulling with a force that's twice as large, then you have to show that arrow twice as long as the arrow going to the left. And so this is basically what free body diagrams are going to look like. They're going to look like arrows drawn from the center dot here, just with their labels. The whole idea, though, is that these diagrams really do help you write the equation. There are a bunch of things I've said so far about these AP diagrams, like drawing motion diagrams or something, and how like the College Board the College Board thinks these diagrams will help you solve the problem, but I don't really think that because like you guys already know this stuff. That's not the case for this. These diagrams really will help you solve the problems. If you haven't written these down already, take a second to pause this video and write down these notes, and when you hit play, we'll move on to our next batch of notes. Okay, now we just really have a bunch of things to say about free body diagrams. Little notes. This one's a big one, though. Big note. To write the equation from the free body diagram, we take the sum of all of the forces acting in the direction of the acceleration, and then you add all those together, and then you hit minus, and then all the forces acting in the opposite direction of the acceleration, and you set that equal to ma. So let's say you had a diagram here where you had two forces, which we'll call F1 and F2, acting to the right, and you had one force, F3, acting to the left. Judging by the diagram here, because the length of the arrows show you the relative magnitude of the forces, we should expect this object to accelerate to the right. And so we can draw a little arrow off to the side showing that it would accelerate to the right. We take the sum of the forces acting in the direction of the acceleration, so that would be F1 plus F2, then minus all the forces acting opposite the direction of the acceleration, that would be F3, and then we set it equal to ma. That's the idea. That's how you write an equation from a free body diagram. And we're going to get like tons of practice with this. I'm just going kind of fast here because I want to finish up the notes section of this before I like show you a real concrete example. A couple of important things to make note of. This is where the little notes start. That right there is a huge note, though, so make sure you write that down. That's like a really consequential piece of information. Free body diagrams do not include the net force. You write that in the equation. The net force is a combination of all the forces shown in the diagram. They do not include components of vectors if those vectors act at angles. And free body diagrams do not include a vector showing the acceleration. Notice, when I showed the acceleration, I showed it off to the side. You are never supposed to have the net force or the acceleration attached to the dot here. That's never supposed to happen. Additionally, we're going to say here, while you're not allowed to show components on like the official free body diagram, sometimes, especially when things are acting at angles like a lot in the problem, it's really important to make a second diagram showing all the components. You'll see that when we get to problems where that really matters. These are all super important things for you to know. Take a minute to pause this video here and write all this stuff down, and when you hit play, we'll move on. Okay, so for the last note, before we move on to an example, and I think this will become apparent when we look at the example, our last note here is, since the free body diagram accounts for the direction, we only have to consider the magnitude of the acceleration. And so the idea here is that the free body diagram itself will take care of the direction, because we are going to sort of include that with an arrow off to the side. Remember, that last note or the last slide had a note that said we don't actually include the acceleration in the diagram, like attached to the dot, but we do show it off to the side. And so since we do show it off to the side, the basic idea is that whatever direction the diagram shows the arrow for the acceleration, well, that's just going to be the direction of our acceleration. And so the idea is the diagram is going to take care of the directions. And so really all we're solving for is the magnitude, because the direction is shown by the diagram. Take a second to write that down, and then I'll show you exactly what I mean when we take a look at an example. Okay, so let's take a look at an example. You're going to get a ton of practice with these as we move on through the unit, but I figured while we're talking about this for the first time, we should at least show a concrete example of what we mean. So let's say we have a situation here where a person is taking their hand and they're pushing these two blocks as shown here in the diagram. And so the first thing that you need to realize is that this person is pushing these blocks on a surface, which is not actually drawn in this particular thing, but it looks something like that, right? It's just a horizontal surface these blocks are sliding on. And the other thing that we should say, and this is really only because we haven't talked about it yet, but we should say there is no friction here because we have not talked about friction yet. And so the first question you really want to ask yourself is, if a person is pushing on these blocks as shown in this diagram, which way are the blocks going to accelerate? And it should be obvious to everybody, these blocks are going to accelerate in this direction over here to the right. So when you're pushing these blocks on this flat horizontal surface, the blocks are going to accelerate over to the right. And so off to the side for all of these diagrams, or underneath, we put a little arrow showing the direction of the acceleration here is to the right. Notice we're not connecting that to the dot because free body diagrams are not allowed to show the direction of the acceleration. And so then what we have to do is we have to draw a diagram of the forces, remembering here that these blocks are sitting on this flat surface. So as we said before, there are a lot of ways that you can think about drawing these free body diagrams, but what's super easy to think about when you're trying to figure out how many forces you're supposed to draw is how many objects the object in question is interacting with. So let's start over here with block B. So if we want to figure out how many forces are supposed to be shown in this particular diagram, what we need to consider is how many objects block B is interacting with. And by my count, there are 4 objects that block B is interacting with. Block B is interacting with the Earth, and so we are going to see a force from that interaction. Block B is interacting with the table, so we are going to see a force from that interaction. Block B is interacting with the person's hand, so we're going to see a force from that interaction. And block B is interacting with block A, and so we're going to see a force from that interaction. And so here's how this goes. The first thing you should pay attention to is that whenever an object is shown on a surface here, like this, you're going to have a normal force, which we'll label F with the subscript N, and you're going to have a gravitational force. And because we know that these objects are equal, because we know that these forces are equal, we're going to try to draw those arrows the same length. Now, if there's a grid space shown in the diagram, then we're definitely going to make sure they are exactly the same length. If there is no grid space, which is going to be the case when we're doing these things on homework, if there is no grid space shown in the diagram, then we're going to want to try to take care to just draw it as close as we possibly can to being the same length, and then we'll move on from there. So as long as they're roughly the same length, we're not going to go too nuts about it. And that's it. Now, when I draw these on like the homework solution sheets, I usually use a ruler. Can't really do that here on my little digital sketch pad, but that's good enough for our purposes. And then, of course, we have to recognize this thing is not accelerating in the vertical direction, so it actually really makes sense that these two forces would be equal, because if these forces were not equal, the object would be accelerating up or down, depending on which force is bigger. And that brings us to the horizontal forces here. In the horizontal direction, we have two forces acting on block B. We have the force from the person's hand pushing to the right, and we have the force from the block A, pushing on block B to the left. And so the first thing you think of when you realize that there are two forces acting in opposite directions on this block here is that one of them is going to be bigger than the other. And we know that one of them is going to be bigger than the other because there definitely is a net force acting on this block, which we know because the block is accelerating. And so now you have to think about to answer this question is which one of these forces is going to be bigger. And the force that's going to be bigger is the force from the person's hand, because that force acts to the right. And the acceleration being in that direction tells you the net force is in that direction, which means the force going to the right has to be bigger than the force going to the left. And so what we draw here is we draw an arrow going to the right, and we draw an arrow going to the left that's shorter. And the arrow going to the right, I'm going to have here listed as F, and then I'm going to write applied. Whenever somebody, like a person, applies a force to any of the objects in the problems, we usually refer to it as the applied force. And so we note that by writing F applied. Eventually, we're going to end up just writing like F and then app for the subscript so we can shorten it up, but that's the basic idea. And then for this force, because it's the force from block A on block B, we can just write FA on B. And that's it for the free body diagram for block B. It should be clear to everybody that this diagram makes sense based on the situation because we see no acceleration in the vertical direction, so the forces should be equal in the vertical direction, and we do see an acceleration to the right in the horizontal direction, and so we see the net force acting to the right in the horizontal direction, which tells us the force acting to the right has got to be bigger than the force acting to the left. So now that we've got the diagram for block B, the diagram for block A should be pretty straightforward. Of course, a good thing to think about before we do these, as we just mentioned before we did the diagram for block B, is how many interactions is block A experiencing? In other words, how many objects is block A interacting with? Block A, of course, is interacting with the Earth, and so we're going to represent that by drawing a gravitational force. And notice here that I'm making this arrow a lot longer than I'm making the arrow for the diagram for block B. And that's because, and we're going to assume, unless we're really otherwise told, that block A has a bigger mass than block B. And since the weight of an object is given by the equation Fg equals mg, we're going to assume that the bigger size of block A means block A has a bigger mass, which means it weighs more. And so that means we're going to want to draw the normal force line the same length. And I'm actually going to run out of room here, but I'll just draw it like that. You're always going to have plenty of room whenever you're asked to draw these. And so, of course, we're drawing the normal force too because, number one, A is not accelerating in the vertical direction. We have no reason to believe that. And number two, because the block A is also interacting with the table. And so we show the normal force coming up. And lastly, block A is interacting with block B because it's being pushed on by block B. And so now here's like really just the big question. How long do we make the arrow for that force? How long do we make the arrow for the force of block B on block A? Well, we make it about this long. And if the question that you have in your head now is why, or how do we know that, the answer is pretty simple, right? We just have to think about the question. How is it that you know the size of the force exerted on A by block B, or the force exerted by block B on block A? And the main idea here is that this force and this force are Newton's third law action-reaction pairs. The force exerted by block A on block B is equal in magnitude but opposite in direction from the force exerted by block B on block A. And because those are action-reactions pairs, they should be shown as being the same size. And that's it. That's the idea. And so just to wrap this up here, this makes sense because our diagrams show in the vertical direction for both objects, we see that the forces are canceling each other out, so there is no vertical acceleration. And we also see the forces not canceling each other out in the horizontal direction, so for both of them, the net force is acting to the right. Now, just to finish this up for today, because this is really the last thing we're doing for today, let's just go ahead and write an equation from the free body diagram. Well, really, what we have to do is do this in both directions. So what we should say here first for block B, for the y direction, we already know what the sum of the forces equation should look like, because the sum of the forces in the y direction is equal to 0. And that's because the blocks are not going to accelerate in the vertical direction. And so there are a number of ways you can do this, and I don't really care how you do it, just as long as you get it right. You can say, if you want, that we have the force going up minus the force going down, so Fn minus Fg, and that's equal to 0. Or you can just say, and notice I'm just going to do this over here because it's going to be the same thing for block A. You can just say here that since we know the sum of the forces in the y direction is going to be 0, that just means all the forces acting up are equal to all the forces acting down. And that's it. Fn equals Fg. Notice, if you add Fg to the other side here, this equation would give us Fn equals Fg anyway. And that's the idea. You write your equation according to the diagram. The normal force here is equal to the weight, according to our diagram. And lastly, we just have to do the sum of the forces in the x direction. And the sum of the forces in the x direction are going to be equal to ma now, because the net force in the horizontal direction exists. It's not equal to 0. And so what we can say for the x direction is that ma, we take ma as we wrote in the instructions, we set it equal to all of the forces going in the direction of the acceleration, which for this block is Fb on A, and we subtract all the forces going in the other direction. And for this one, there's nothing, and so that's our equation for block A in the x direction. For block B, it's a little complicated, but still, we say that the sum of the forces here are going to be equal to ma, and we'll write that ma is equal to the forces going in the direction of the acceleration, which is F applied, and then we'll subtract the forces going opposite the direction of the acceleration, which is Fa on B. And that is it. And so what you should notice is that now, essentially, what all of these problems turn into is a system of equations problem like you see in math, where you have two equations with two unknowns, the unknowns here being the acceleration and the mutual contact force, A on B and B on A, probably because they would tell you what the force exerted by the person's hand is. And so the idea here is that you would solve these equations simultaneously and get both answers for the acceleration and for this action-reaction force. And of course, the way that you would do that would be depending on what works best for each equation. You can solve it by substitution. You can solve them by addition. There's a lot of ways that you can solve these system of equations, and so that's what I will focus on as we move through each individual problem, like what the best method is, depending on how the equations look from the diagrams for each particular situation. But with that, that's it for today. Tomorrow, we are going to take a look at the first kind of problem that we are going to be using these free body diagrams for, and talk about how we can write the free body diagram, or I should say draw the free body diagram, write the equation from the free body diagram, and then use those equations to solve for the things we need to solve for. All right, everybody. Take care.